guys. Happy Monday. I just wanted to let you know we're going to continue what we were doing Thursday or Friday, I can't even remember, with lesson 33 and more graphs of polynomial equations. We're going to talk some of this you can read. I'll try to make it as easy and painless as possible. I'm on page 178. So I'm going to start with polynomial equations. We don't talk about them a lot, but we do like to sketch graphs. Okay? Number one, graphs of polynomial functions are smooth, continuous curves that have no holes, no breaks, and no sharp points. They're continuous and they are functions, meaning they have no holes or anything. Okay? In bold, the turning point theorem tells us that the graph of a polynomial function has fewer terms than the degree of the polynomial. Okay, so I'm going to make some hints here. Okay, so what's the degree of a polynomial? I don't want to assume that you know all of this. What's the degree of the polynomial? It's the highest exponent. Get all those extra dots off. My eraser was very large. Let's turn it down. Okay, the highest degree, the highest number. Meaning, if I have x cubed plus 5x minus 2, okay, what is the degree of this polynomial? Okay, it has a degree of 3. Okay, so if it has a degree of 3, the turning point theorem says it can have at most 2 terms where the graph can change up and down. Okay, so it will turn. Okay. If I have an x squared, think of your parabolas. Okay, how many turning points does it have? Let's stop. What do I mean about a turning point? What does that mean? The turning point of a polynomial equation. Okay, let's scroll down just a little bit. The turning point is when, if we have an x squared, when it changes from increasing to decreasing, that's a turn, or from decreasing to increasing. Okay, so that's a turning point. That's what I mean at most 2 turns. Okay, so if I have an x squared, okay, it's decreasing. It has a turning point to the point where it will increase. So my one turning point would be the vertex. Okay, does that make sense? So a cubic up here with a degree 3 can have at most 2 turns. So if it comes up, it can go up, it can turn. So here's the turning point, and then it can go down and it can turn up again. So it can have at most 2 turning points. Okay, 2 places to change direction. So what if I have a to the 5th power? How many times can it turn? It can turn 4 times if I had a 5th. Okay, I'm going to go to another page so I don't mess this up too much. Something else we need to talk about is the direction. So on page 178, you see a y equals negative x squared plus 4x minus 3. Okay, few things that we notice about this graph. Okay, they go ahead and graph. I'm scoot it over just a little bit. It has a y-intercept of negative 3. Okay, there's something I hope some of us remember about this negative sign in front. What in the world can that negative sign mean? Maybe you remember it. Yes, it means it's going to be facing down. It's going to be an upside down parabola. Okay? upside down parabola, they go ahead and graph this for you, which we'll talk about in just a minute, how to find that vertex. Ooh, I did not go through -3. So it can have at most one turn. And if that degree, whatever your highest degree is, yeah, I know, I'm low battery. I need to plug it in. Sorry about that. If it's a negative, it will have the opposite way a normal one does. Okay, so it's going to be downward facing. Okay, so whatever your highest exponent is, that's the coefficient we're looking at to see, is it upward facing or is it downward facing? Okay, we have a cubic function that they graph. Normal cubic functions, y equals x cubed minus 3x squared plus 5. Normal cubic functions start down. Actually, we could even say all odd exponents, okay? Just like 2 squares, we could say with all even exponents, they're going to have the same characteristics. We'll start down, come up, and sometimes come back down and go like that. It can have 2 turning points. That's a normal x cubed function, okay? We'll get into how we can find the other pieces of this later about these turning points, the vertices, okay? But let's just note cubic functions start down. Start down, end up, okay? No matter what, they will start and end in the same direction. All odd degrees will do the same thing. All the odd degrees will start and end in opposite directions. Oh, I cannot write today, I'm sorry. Opposite directions. So if it starts down, ends up. Okay, that's the way they normally will go. If it was a negative x cubed, what if I did a y equals negative x cubed? Okay, means it would start at the top, come down, it might have 2 turns, and it's going to end down. Okay? Now that's not exactly x equals y equals negative x cubed. It's probably plus something else, okay? Not anything that, I know it's not this either. It's got some other stuff with it. Okay? I didn't do an exact graph. Okay, so could I make the same distinction with even exponents? Even degrees. Let me say degrees and not say exponents. I need to stop with that. Even degrees polynomials will always start and end in the same direction. Think of your parabolas. They either both go up or they both go down. Okay? They do an x to the 4th. It can have at most 3 turning points. Okay? And it kind of looks like a W. And then they give you which of the following function is most likely to produce this graph. You could count the turns. 1, 2, 3, 4 turns. So it can have at most an exponent of 5. So all of these have a 5. Now, do they start and end the same direction? No. It has to be an odd degree because they start and end the opposite way. So it can only be x to the 7th or the x to the 5th. Now, what do we need to look at? Is it a negative, like this one is, or is it a positive, like the pink one is? You're right, it's negative. So it has to be h of x, the negative x to the 5th. Okay? That's the type of question they're looking for. It's not greatly in depth yet. All right, so they show you x cubed and a negative x cubed to be, it can look almost like a straight line. You know how I said this is not really an x cubed function? I'm going to go to another page. Because a regular x cubed is not that glamorous. A regular x cubed starts at 0 and it comes up like this, and it goes down like that. There is no real turning point. The turning point goes from, let's talk about a frowny face to a smiley face. Okay? That's its turning point. Okay? If we start adding the 2x plus something else, that's when it changes and gets more turns. Okay? So then they have an x to the fourth, and x to the fourth can simply look like a parabola. It can. Okay? I'm going to skip and let you look at some of those graphs. Then I'm going to go down almost to the very bottom of this page where it talks about polynomial functions, a to the n. So n is our highest degree. So here we go. N, that they're going to look at, is the highest degree, or the degree of our polynomial. Okay? The a is the coefficient with the highest degree polynomial, highest x value. Variable, maybe that's the way I'll say it. It's your coefficient. Okay? And b is going to be the coefficient of the next one. Okay? B will be the coefficient of the next highest degree. Okay? Mean they give you a long f of x. Here we go. I'm going to write it at the top. F of x equals axn plus bx to the n minus 1 plus cxn to the n minus 2 plus et cetera, plus some constant k. Okay? Okay, yes. So now they talk about an x bar. Okay? X bar is not greatly huge to us, but will be a little bit important if we want to find those vertices. Okay? X bar is equal to whatever b is over, it's negative also, NA. So it's a negative b over NA. We've heard b over a before. Okay, at least I hope you have. Okay, in Algebra 2. So for a quadratic, it's a squared, okay? For a squared, this value will simply be the x value, x bar is equal to the x value of the vertex. B over 2a, does that ring a bell? That's why n is 2, negative b over 2a. Okay? For a cubic function, okay, the x bar will be a little bit different. The x bar will equal the x value of the inflection point. Meaning where it changes direction. Okay, the inflection point. Okay, for the fourth, they call it a quartic, which is a fourth degree. Okay, the x bar gives us a good idea. Okay, x bar gives a good idea. It's not necessarily the exact value. It gives a good idea of the x value of the center of the graph. Not exactly. And after the fourth, it really doesn't tell us a whole lot, okay? So we've got these three pieces and this formula, okay? So when they ask you to sketch the graph of, they don't want any great, huge details, okay? So here we go. We're going to try to finish this lesson. I'm sorry if it's a little bit long. Y equals negative x cubed plus 3x squared minus 2x plus 3. So we have a cubic function. So how many terms can it have? You're right, it can have 2. Is it positive or negative? It's negative, which means we're going to start up and we're going to end down. Okay, some of the logic things that should be in your brain. Okay, should you have a y-intercept? If x equals 0, okay, if x equals 0, oh goodness, sorry, x equals 0, what does y equal? I kind of just gave it to you. 3, okay, that's our y-intercept. So we can do a lot of things just by the logic in our brain, okay? Then if we add something to find our inflection point, like that last equation, so x bar equals negative b over NA. I'm going to go ahead and just write that again. What is that? X bar equals negative b, which is 3, over n, which is 3, and a, which is 1. Okay? 3 times 1, that's not 31, sorry. So negative 3 over 3. Why do they have it positive? It shouldn't be positive. Because 1 is negative. I got it. Never mind. Times A. A is negative 1. All right. Sorry about that. So that's negative 3 over negative 3, which is simply 1. Okay? So that x equals 1. Can we find that that's our x value of our turn or our inflection point? So that's x equals 1. So if x equals 1, what does the y equal? Okay, so I'm going to go back to my equation. Negative 1 cubed plus 3 times 1 squared minus 2 times 1 plus 3. Okay, to find this point, 1 cubed, so I've got negative 1 plus 3 minus 2 plus 3, so I've got 2 minus 2 is 0, 0 plus 3 is 3, y equals 3. So I have another point of an inflection point where it's going to change direction. I've got a lot of stuff. I'm going to try to squeeze in the sketch of my graph. So I'm putting in the points that I know. I know if x is 1, y is 3. And at that point, it's turning. Okay? I also know if x is 0, then y is 3. It's another point. Okay? So, inflection point. Inflection point is not necessarily where it turns. It's going to be, remember when I talked about the smiley face and the frowny face? The inflection point is going to be that point, where it changes from a smile to a frown or a frown to a smile. Okay? So, looking at this, when there are 2 points here that are this close together, I'm having to think that my turn will go in between those points. Okay? So, we know it has to start up. So, I know it's coming somewhere to here. Okay? Coming to here, it's probably going to go down. It can look a lot of different ways. Oh, goodness. Let's kind of pretend that wasn't the same. And then, see here, all of this is smiley up. I went a little below, and then we're going frowny down. Okay? I don't know exactly what that's going to look like. If you turn the page, they give you 2 different possible examples. Okay? They didn't include the y-intercept, in the second one, so we know it has to go through this one. Okay? So it could go even farther, but then it turns and goes that way. That's a sketch. It's a very rough sketch. We don't know exactly what it looks like. Okay? All right. So we're just going to do a few problems from lesson 33. All right. We're simply going to do number 3 through 9. Numbers 3 through 9. And we're actually going to pause. We're not going to do a ton. We may come back and do some more, but not even going to say it yet. All right. Love you guys. Have a happy rest of your Monday. We'll talk to you later. Bye.